All right, this lecture video, what I'm going to do is I'm going to review some of the fundamental concepts that we have thus far discussed about the economics of pollution, present to you a taxonomy or a general vocabulary that we will use to describe various types of pollutants, and then move on to describe what the U.S. experience has been attempting to regulate pollution and achieve greater air, water quality, etc. And then maybe take a second at the end to discuss a little bit about the unique problems of dealing with mobile source pollution. All right, so to begin, let's first just discuss some of the basic general terminology that we use to describe various types of pollutants. It's important for us to understand all the various types of pollutants because, as we have mentioned in class, oftentimes the policy, specifically the optimal policy towards a given pollutant, will be very much defined by the type of pollutant, the amount of damage it creates, what sort of damage it creates. Is it a sort of loss in profitability of firms, or is it a reduction in human health? And then also, where do we actually experience the pollution? How is the pollution experienced itself? We've already mentioned in class the sort of two broadest definitions of pollutants, stock versus fund pollutants. If you'll recall, stock pollutants refer to pollutants for which the earth has no absorptive capacity, so every unit of a stock pollutant damages the environment in some way. And then with fund pollutants, these are pollutants for which the earth has some absorptive capacity. This means that a fund pollutant can be emitted up to a certain point, usually what we'll refer to as a threshold, before it begins damaging. So what we mean by stock is every unit damages, and with fund there is some amount before damage starts to be realized. From a local versus regional perspective, this is obviously a big issue when it comes to air pollution. You have local air pollution. This tends to be particulate matter pollution that is more acute and near the source. So, like, for example, near a coal-fired power plant will oftentimes have its own unique local pollution. Additionally, the coal-fired power plant will almost certainly produce regional pollutants by emitting some of that pollutant out into the atmosphere. So we want to start thinking about pollutants in terms of their behavior. And along this line, of course, there are mobile sources of pollution and there are stationary sources of pollution. Some pollution, once it's emitted, moves to all sorts of places, while other pollutants tend to stay in a given area. For example, air pollution is almost always mobile to some extent, even if it's only mobile to a regional perspective. But air pollution can also be a global pollutant. So, CO2 that's emitted in New York City has the same climatic destabilizing potential as CO2 that's emitted in any other country, because that CO2 moves up into the upper atmosphere. Stationary pollutants tend to be pollutants that are the result of some form of environmental problem, like a spill, for example. An oil spill will tend to produce pollutants in a stationary capacity, meaning that the pollutant is, say, released into the ground. Maybe a pipe has burst, and the pollutant does tend to stay in that particular area. However, even stationary pollutants can become mobile pollutants. For example, if you have an oil spill and some of that oil makes it into a river, which flows downstream, and now what you have is a situation where a previously stationary pollutant has become mobile. And as a result, policies in order to reduce these types of pollutants need to be cognizant of both the mobile and stationary components of any given pollutant. There are also pollutants for which we know exactly where the source of the pollutant is. Those are called point source pollution sources, meaning that we know exactly where the pollution began. And then we have other pollutants for which there is no real way for us to know what the initial source of the pollutant tends to be. Your point source pollutants, these tend to be pollutants which are nearer to the ground. We'll discuss those in just a moment. Your non-point source pollutions tend to be mobile pollution, meaning that it's either atmospheric pollution, such as like CO2, where we can't really pinpoint the source of the pollution at a given place, but we know that there are a multitude of sources of that pollution, perhaps in a given region. For example, a highway interstate system produces a tremendous amount of pollution. However, the sources of that pollution are mobile, the automobiles, and as a matter of result, it can be very difficult for us to understand the source of that particular pollution. I mean, we know that it comes from cars, but from an ability to use policy to reduce that particular pollution, it's very hard for us to, for example, cordon off a section of an interstate and say this is where the pollution is occurring, because in reality the pollution is occurring across the entire interstate system. So we can generally think about the process of how a pollutant makes it into the environment and then produces damage. In this particular figure, what you have over to the right is what we call the emissions load. This is the increase in the emissions that is occurring due to economic activity. Then you have that flowing into the overall pollutant accumulation. And again, here what we're referring to is a singular pollutant. So if you can imagine in this diagram, what we would be envisioning is a particular type of pollutant, say, for example, sulfur dioxide, which produces smog. And we can look at the amount of sulfur dioxide that's being emitted to the overall level of sulfur dioxide in the atmosphere. So again, we can look at that from the perspective of the total accumulation. Then we consider what part of the pollutant accumulation is successfully absorbed by the environment, and to what extent is the pollutant accumulation then translated into damage. So the way you can think about it is that emissions are released into the environment. They accumulate over time. Some of this accumulation might be absorbed by the environment in some way, and that which is not absorbed by the environment is instead flushed out in the form of damage. Again, in the context of stock pollutants, there is no absorptive capacity, so the emissions load and the pollutant accumulation translate directly into pollution damage, whereas with a fund pollutant, there is some absorptive capacity for the environment, and so some of the pollutant accumulation is transferred in that particular way. However, even under fund pollutants, we expect some form of pollution damage. Another important distinction to make is how we think about the pollution. We refer to this as zones of influence. The horizontal zone of influence is essentially how much does the pollutant spread out? How wide is the damage of the pollutant? Is this an acute local pollutant, or is this a pollutant that has a much wider regional damage influence? The vertical zone of influence refers to whether the damage is occurring at ground level or even sub-ground level in the case of, say, water table pollution, or if the pollution is instead making it up into the upper atmosphere, as is the case with pollutants such as carbon dioxide and such. In reality, there are pollutants that exist at every particular level. So take the vertical zone of influence, for example. You have water contamination in groundwater tables. That, of course, is subterranean. You then have ground level pollution. This would be like, for example, plastic being discarded and not being recycled that just kind of sits on the ground. Then as you move into your air pollution, you start having your particulate matter, your PM 2.5, your PM 10.0. These tend to exist a little bit above ground. They actually, this type of pollution tends to exist sort of, near your breathing. So it's a little bit off the ground, but it's not quite into the atmosphere. Then you have your sulfur dioxide. This happens much further up in the atmosphere, generally away from our breathing, but still close enough for us to directly see it in the form of smog. And then, of course, you have CO2, which makes its way up into the upper atmosphere. So you can think about pollution in the context of how wide it is, and in terms of its horizontal zone of influence, and then where in the context of this vertical zone of influence the pollution is actually being experienced. So now what we want to do is we want to discuss sort of what is the optimal pollution. That is sort of the point of this particular class in environmental economics, is for us to envision that for society there is some level of optimal pollution. And again, this can be a fairly controversial topic. Those among us who are a little bit more environmentally inclined, we tend to see any pollution as being inherently problematic. But of course, from an economic perspective, so much economic growth requires some level of environmental churn, some level of environmental disruption, that the goal is not to reduce pollution to zero, but instead for us to find an optimal level of pollution. And of course, how we define optimal is very important. So with respect to stock pollutants, the basic idea is that because every unit of a stock pollutant increases the damage, in other words, damages are increasing for every individual unit of stock pollutant that is emitted, then the optimal amount of emissions is going to be essentially a net present value problem. So what we consider is we want to maximize the net present value of the stock pollutant. So for the goods that cause the stock pollutant to be emitted, we would use a net present value calculation where we essentially take the benefits of the good, for example, bottled water, which produces plastic, which is a stock pollutant, and we would subtract off the cost. Here the cost would be the damage produced by the stock pollutant, and then we would consider that over some particular time horizon. We can consider it over a few years, or we could consider it over a millennia. It doesn't really matter necessarily. We consider it over a certain number of years, and then the goal for us is to maximize the net present value. Obviously, as we use more of the pollutant, for example, plastic water bottles, the benefit of the plastic water bottle goes up. However, at the same time, because it is a stock pollutant, the cost of using plastic water bottles is also going to rise. And so there is a classic trade-off here in the context of the net present value. The trick here, of course, is for us to establish, what are the damages that arise from the particular pollutant, and having an honest understanding of what that damage means. If we don't know the monetary value of the damage, then it's hard for us to compute this cost benefit. So if we go back to our previous conversations about non-market valuation, this is where it's incredibly important for us to have an understanding of the economic value of environmental damage, because without the economic value of environmental damage, we can never hope to make this particular calculation. And if we can never make this particular calculation, then there's no way for us to maximize the net present value of that particular good. However, if we do have an understanding of the monetary damages of a particular pollutant, and we have an understanding of the economic benefits of the goods that produce that particular pollutant, then the ability of us to extrapolate out into the future is actually fairly straightforward. So all we need to do this calculation is we need the benefits of the pollutant, and we need the costs, the damages caused by the pollutant. Generally, the benefits of the pollutant are going to be determined by the private market. The costs, the damages of the pollutant are going to be determined by scientific research. How much does every plastic water bottle cost in the form of environmental damage? And as we've already discussed, the main problem with cost-benefit analysis is the fact that there's a lot of uncertainty. We'll talk a little bit later about this notion of uncertainty and what happens. Like, what happens if the benefits change over time? What happens if the damages change over time? Maybe we invent some new form of plastic which is less environmentally damaging than previous forms of plastic, and maybe that means that the optimal amount of plastic has increased over time. That could certainly be a possibility. But it's important for us, again, to have an honest understanding of what the benefits of the goods that produce the stock pollutant are and what the environmental damages of the stock pollutant happen to be. Otherwise, we cannot hope to arrive at the optimal amount of pollution. Fund pollutants, because there is this threshold for which they do not create damage, this implies that up to this particular threshold, or even a little bit beyond it, is likely going to be where our optimal pollution for fund pollutants happen to be. This means that we will take on a cost minimization approach. In other words, we want to minimize the damage costs, that is the environmental damage, and we also want to minimize the abatement cost. The abatement cost is the amount of money spent on reducing pollution. Again, because the environment has some absorptive capacity for fund pollutants, from a certain perspective, you could over-regulate these types of pollutants. You could reduce these pollution levels to be so low that you're not getting any economic benefit from them, and also they're so far below their damage threshold that they're not actually even causing any problems. Now, again, if you come at this from a strictly environmental perspective, this may seem like a useful option to you. Let's just get rid of the pollutant completely. But again, if the product is something which is extremely economically important, say for example carbon dioxide, then we have to ask ourselves, is it even feasible to drive carbon dioxide emissions to zero? And if not, okay, then what's the next best option? The next best option is for us to identify the optimal amount of CO2 and then construct a policy that gets us to that optimal amount. This is where we rely upon the equimarginal principles that we discussed in the previous video. The first equimarginal principle, which is the rule that we'll use to determine the efficient level of pollution for a given pollutant. If you have not watched the previous video on the first and second equimarginal principles, you should do that before proceeding in this video. So the basic idea behind the first equimarginal principle, which is presented here a little bit differently. In the previous video, I presented it as the marginal benefit of the pollutant versus the marginal damage of the pollutant. Here we can think about it a little bit differently. So instead of marginal benefit from the pollutant, we're going to consider the marginal control cost of the pollutant. In other words, this is how much on the margin it would cost us to reduce the pollutant. You can see that declines as we reduce pollutions more and more. This line refers to the damage cost. This is the amount of environmental damage that is arising because of the pollutant. You can see here that we're assuming that marginal damage costs are increasing and that marginal control costs are decreasing. And so the first equimarginal principle tells us that the most efficient level of emissions is going to be found at the intersection of these two lines, where the marginal control cost is equal to the marginal damage cost. Okay, and again, just to kind of take you through this, the idea here is for emissions levels below Q star, you should see that control cost is greater than damage cost. This means it would cost us more to reduce the pollution than what we're paying in the form of environmental damage. So again, assuming that we know what the monetary value of the environmental damage is, and assuming that we know what the monetary value of pollution control is, we can see that below Q star, the amount it costs us to control this pollution is greater than the damage that's being caused by it. Therefore, it makes sense for us to allow the pollution to rise to Q star. And then beyond Q star, we see that now the damage costs per unit are higher than the control costs, so it no longer makes sense for us to allow emissions beyond Q star. So this establishes for us the most cost-effective way, this establishes for us the least cost level of pollution. Again, the first equimarginal principle says that the least cost level of pollution will be found where the marginal control costs or marginal benefit is equal to the marginal damage of the pollutant. Damage costs are externalities. So when we talk about damage costs, what we mean is the cost of the pollution. The control cost, the money spent by firms to reduce their externalities, however, is not considered a part of that externality. Sometimes students get confused. They think that the damage caused by the pollutant, as in addition to the amount of money it costs to reduce it, would be considered the externality. Because in a sense, the pollution is hurting society, and then controlling the pollution is hurting the business or whoever is reducing the pollution. But remember that from our perspective, the externality, the environmental damage, is the cost of pollution, while reducing pollution is not part of that externality. This also means that firms that abate unilaterally are placed at an economic and competitive disadvantage. So again, on a private market, we don't expect firms to unilaterally, on their own, reduce their pollution, because it puts them at a competitive disadvantage. If you're a firm in a market and no one else is reducing their pollution, you are not economically incentivized to reduce your pollution either. This is, of course, what creates the initial market failure that we refer to as a negative externality. The private market will fail to generate the efficient level of pollution, and therefore this punishes firms that abate their own pollution. We also saw in the previous video that we can actually get at the most cost-effective allocation of pollution reduction. So that this is, once we've used the first equimarginal principle to find the optimal level of pollution for society, we can then use the second equimarginal principle to find the cost-effective allocation of that abatement across firms. In other words, how much each firm should actually reduce their should actually reduce their pollution. And in this perspective, once we've established the optimal level of pollution, as well as the cost-effective allocation of abatement across firms, we can either use an emission standard, what we call the command and control, which is a mandate that says firms are not allowed to emit beyond a certain amount, or we can rely upon market-based mechanisms such as emissions charges, which again seek to internalize the externality. Okay, so in this figure, what you have is you have two firms, firm 1 and firm 2, and you have their marginal control cost curves. These are the curves that describe the amount of money it costs them to reduce their own pollution. Okay, so if you look over here, you can see we have emissions reduction here for source 1. So as we increase to the left, this is firm 1 abating or reducing more pollution, and as we go from right to left, this is firm 2 reducing their pollution. Okay, and to understand this graph, let's start all the way over here on the right. Here, at this point here at the very corner, this would see firm 1 reducing their pollution by 0 units, with firm 2 reducing their pollution by 15 units. And again, remember, the standard is 15 units. The government wants to reduce pollution by 15 units total across the two firms. And we can see at every point here, you have a combination of abatement across the two firms, which equals 15 units. So at this point, where firm 1 is not abating anything and firm 2 is abating 15 units, what we can see is that the marginal control cost for firm 1 is basically 0, right? Whereas if we were to extend this line all the way up to here, we would see that the marginal control cost for firm 2 is very, very, very high, right? So now we move on to this point where firm 1 abates 1 unit and firm 2 abates 14. Again, we see that the marginal abatement cost for firm 1 is much lower than it is for firm 2. So from a cost-effective perspective, it doesn't make sense for firm 1 to just reduce their pollution by 1 unit and firm 2 to reduce their pollution by 14 units. Okay, this is not cost-effective. Okay, as we move this direction, what you'll notice is that now firm 1's marginal abatement cost starts to get closer and closer to firm 2's marginal abatement cost. And from a social perspective, again, this is the least cost point, meaning that it is the least cost option for firm 1 to reduce their pollution by 10 units and firm 2 to reduce their pollution by 5 units. Okay, this is the least cost. So in other words, if 15 units of pollution is optimal, 15 units of pollution abatement is optimal, then it is also optimal, and in this case, least cost, for firm 1 to abate 10 units, while firm 2 abates 5 units. Okay, we see that if we go beyond this point, now where firm 1 abates 11 and firm 2 abates 4, again we can see that the marginal abatement cost for firm 1 is now higher than it is for firm 2. Okay, so again, we have two policy options now open to us. We can mandate to the two firms that we want to reduce pollution by 15 units, and let's say that we use the second equimarginal principle to establish the least cost allocation of that abatement across the two firms. Here, firm 1 abates 10 units, firm 2 abates 5 units. However, this would be fairly difficult to do. Right? This would imply that regulators understand the actual abatement costs of the two firms, as we generally assume in these sort of social planner theoretical frameworks. However, in the real world, oftentimes regulators don't necessarily know the full cost structure amongst all the firms in a given polluting industry. Now, do we need to know what the costs are? Not necessarily, and let's see why. Okay, so this is the same graph as before, except instead we just have the marginal abatement cost curve for firm 1. Okay, this is the same T as before. Okay, notice we just have T here, same T. Okay, firm 1 abating 10 units. Now, the idea is that instead of mandating to the two firms, you abate this amount and you abate this other amount, or we could split up the abatement goal. So if the abatement goal is 15 units of abatement across the two firms, we could have each firm reduce their pollution by 7.5 units each. We know this is not cost effective. Again, if you watch my previous video, we know that the cost effective environmental policy will be the one that uses the second equimarginal principle that equates the marginal abatement costs, the marginal control costs across the two firms. So now let's consider T here as a tax, or what we might call an emissions charge. Okay, so imagine that every time a firm emits pollution of a particular pollutant, every unit of it, they have to pay T. Okay, they have to pay T amount of money to do it. So imagine a Pagovian tax set on a particular pollutant. Now, if that tax is set into this given market, here's the way the decision making goes for the firm. Now realize this does not require that the regulator or the government know the control cost of the firm. All this requires is that the government sets a tax and then allows the firm to respond to the tax. Okay, so imagine that we start over here to the left, and with the firm currently not reducing pollution at all. Okay, so imagine they're letting their smokestacks go crazy, right? No pollution abatement whatsoever. But notice that the tax is much higher than their control cost. Okay, this means that they actually could save money by reducing their pollution, right? Because if they reduce their pollution here to, say, from 0 units to now abating 1 unit, you can see that this is much cheaper than paying this tax, right? This is true all the way up to this point, right? Up to this point, the tax is more expensive than the control cost. Therefore, it makes economic sense, it makes profitable sense for the firm to abate these units of pollution up to the point of the tax. And then beyond that point, now the marginal abatement cost is greater than the tax, which tells us that the firm instead would prefer to just pay the tax. Okay, so if I tax this firm for each unit of pollution that they emit, okay, what the firm will respond by is that they will reduce their pollution by 10 units, and then beyond 10 units, they will pay the tax on that pollution. So for example, if this firm was previously emitting 20 units of pollution, Okay? They will respond to this tax by abating 10 units of pollution, thus reducing their total level of pollution down to 10 units. Okay, again, this is all about economic feasibility. Okay, for abatement levels below 10, the tax is greater than marginal abatement costs, so the firm would rather abate. Beyond 10 units, the tax is less than the abatement cost, so the firm would rather pay the tax. Right? So the government sets an emission charge, a tax into the market. Each firm in the market then responds in their profit maximizing way. Again, this is cost effective. So prior to their optimal abatement level, the tax will be greater than the abatement cost. And then after their optimal abatement level, their marginal abatement cost will be greater than the tax. We've previously also discussed cap and trade programs. The idea behind a cap and trade program is the government establishes a cap on emissions. So from our previous example, that cap could imply that we want the industry to reduce emissions by 15 units. And then the government creates what we call pollution permits. Each permit allows firms to emit their a level of pollution, and you can't emit the pollution without the permit. Some of the assumptions of a cap and trade program, in other words, the assumptions we need to be true for a cap and trade program to work. First off, the permits need to be auctioned off or allocated by some criterion. In fact, one particular problem with a lot of modern cap and trade programs is that they suffer a similar form of cronyism that we see in all sort of forms of government where, friends of particular politicians, their businesses will often receive more pollution permits than would be sort of socially optimal for a perspective. So one of the assumptions of a cap and trade program is that we need the program to auction off the permits in a sort of private market setting. The permits need to be freely transferable. That means amongst firms in a given industry, they're allowed to trade their permits costlessly. And the number of permits initially allocated must achieve the optimal pollution conditions previously discussed. Okay, this is the same figure as before. We have the marginal control cost for firm 1 and the marginal control cost for firm 2. Now, the idea, again, is let's start all the way over here to the left, where firm 1 is abating nothing and firm 2 is abating the full standard. And again, the idea here is that the government has set a cap at 15 units of abatement across the two firms. What you notice, again, is that at this level of abatement for firm 1 and firm 2, it's much more expensive for firm 2 to be abating this level, this additional unit of emissions than it is for firm 1 to abate it. What that means is that assuming that firm 1 has pollution permits it could sell to firm 2, there's a clear bargaining opportunity between the two firms. Firm 2 is going to say, hey, wait a minute, for reducing my emissions by a single unit from 14 to 15, so as I increased my abatement from 14 units abated to 15 units abated, firm 2 is paying an astronomical cost to do so, right? Whereas if firm 1 were to increase their abatement from 0 to 1, you can see that their cost is very, very, very small. This means that there's this entire gap, right, from this point all the way up until we would hit the marginal control cost for firm 2, in which there is a potential permit price that both firms would agree on. Okay, and this is true all the way up to the intersection. Okay, let's look at this for example. Let's look at the situation where firm 1 abates 8 units and firm 2 abates 7 units. Okay, we see that this is not optimal, that our optimal position is for firm 1 to abate 10, while firm 2 abates 5. Okay, so the question is, how does natural market forces get us to this point? Well, here's the way it works. Firm 1, again, is willing to sell to firm 2 pollution permits. Why? Because it cost firm 2 this amount in marginality to reduce their pollution from 9 to 8, right? Very high, higher than the abatement cost for firm 1. This means that it would be cheaper for firm 1 to abate, instead of 8 units, to abate 9 units, and that they would be willing to offer a pollution permit price that firm 2 would accept. That basically would be less than the control cost firm 2 would face if they instead controlled this additional unit of pollution. Okay, so firm 2 pays in marginality C to abate the 7th unit of pollution, while firm 1 pays A to abate the 8th unit of pollution. This means that firm 1 would be willing to sell to firm 2 a pollution permit between the prices of A and C, and that firm 2 would accept a pollution permit price between A and C. Now the question becomes, what is the optimal pollution permit price? In other words, what pollution permit price achieves the socially optimal level of abatement across the 2 firms? And the answer is B. This is the pollution permit price that would get the firms, firm 1 to abate 10 units and firm 2 to abate 5 units. And again, this is all based on relative costs. And we can go beyond, right? We could do the same type of logic if we looked at abatement levels over here to the right, where firm 1 has much higher marginal control cost and firm 2 has much lower. Here, firm 2 would be willing to sell to firm 1 pollution permits, and we would move in this direction. And again, the optimal solution is found according to the second equimarginal principle. Now, the key takeaway here to notice is that the optimal pollution permit price, B, is the exact same thing that we saw here. In other words, the optimal Pigovian tax that creates this outcome is the exact same amount of money as would be the optimal pollution permit price, which should make sense to you because the whole point of the Pigovian tax is to get firms to internalize the externality. Therefore, that's how a cap and trade program would work as well. In both instances of a Pigovian tax and a cap and trade program, what we are in essence accomplishing is getting firms to internalize the damages created by their emissions and then allowing natural market forces to seek out the least cost abatement strategy. And again, in this scenario, the least cost abatement strategy is for firm 1 to abate 10 units and for firm 2 to abate 5 units. One particular problem with this idea of thinking about optimal pollution, and there are a number of problems associated with this way of thinking, is that it's always known what the actual optimal level of abatement is, either by using the first equimarginal principle to establish the optimal level of pollution, and then using the second equimarginal principle to establish the least cost allocation of abatement across the 2 firms. So here what we're envisioning is water pollution, and specifically water pollution that occurs into a stream. Each of these represents sources of pollution, and R here refers to the receptor, that is the monitor of the pollution. So we're actually measuring the pollution here. Now the problem is that the amount of pollution that is measured here is defined by where these ports, we're going to call them ports, are located. If, for example, this receptor is here, or if there are ports beyond the receptor and the stream flows in this particular direction, then it's potentially going to miss pollution, which means we're not going to have a full accounting of the total amount of pollution that's occurring in this particular stream. So one of the problems with the optimal pollution strategy is that it can be dependent upon how we're actually measuring the pollution itself. For pollutants like carbon dioxide, in which we can have a relatively accurate measure in the upper atmosphere, it's much easier for us to measure those sorts of atmospheric pollutants. Even though they tend to be mobile, and even though they're global, we still have a pretty easy way of measuring them because they move up into the upper atmosphere in that vertical zone of influence, and then we can measure them when we get up there. However, with other mobile sources of pollution, such as river pollution or stream pollution, we are dependent upon where the actual environmental receptor, that is the monitor of pollution, is actually situated. So this is just a bit of a caveat to this discussion about optimal pollution, right? There's a litany of issues with respect to this sort of optimal pollution argument, right? You have to have a good understanding of what the amount of pollution is. You have to have a good understanding of what each unit of pollution causes in the form of damage, and you have to have an understanding of what each unit of pollution costs if it's abated, which can be very difficult to do if we're in a situation like with water pollution or with a mobile source pollution. Other problems with the optimal pollution strategy is that the regulatory environment may change over time. So, for example, if you use emissions charges or Pogovian taxes, what you may have is over time new firms enter a market and you actually get an increase in the number of emitters. What this means is that you're going to see an overall increase in the level of pollution despite the presence of a tax. So one of the limitations of emissions charges or Pogovian taxation is that if new firms enter the market, the tax itself is going to have to be changed. Otherwise, you're actually going to just simply get another increase in pollution. And again, remember that the idea is that a Pogovian tax is set such that it produces the optimal amount of pollution for society. So under a tax regime, if new firms enter the market, pollution is still going to rise, which of course is a problem if the tax is set such that you are assuming you're at an optimal level of pollution. In a cap and trade program, this is not a problem. Because in a cap and trade program, what you're doing is you're capping the emissions. You don't increase the cap if new firms enter the market because, again, the cap is relative to the social efficiency of the pollutant, right? You're basing this on human health. You're basing this on environmental health, right? So a cap and trade system does not suffer this particular problem. It does not have to be altered in the face of new entry into the market. It may require additional pollution permits to be purchased and sold amongst firms, but you don't even increase the number of pollution permits because, again, you don't want to actually increase the amount of pollution. As inflation occurs, this can affect the permit price and result in higher permit prices over time. So there has to be some accounting for inflation and other various, monetary changes that tend to occur. As technology improves, this is going to change the marginal abatement cost functions. So, for example, if we go back here, we know that as the firms invest in cleaner technology, you may see these marginal control costs fall. And as a result, if the marginal control costs fall, then this could change the permit prices that ultimately occur, and also lower the abatement cost, but at the same level of control. Now, price volatility. The nice thing about a Pogovian tax or emissions charge is that it does not affect those things. So price volatility avoids affecting that, but it does affect allowances in a cap and trade program, for example. And again, uncertainty is always a really big problem in environmental policy. Determining the best policy, whether it's command and control, whether it's market-based, and then whether you're going to use an emissions charge like a Pogovian tax, or whether you're going to use a cap and trade program, is really based upon your knowledge of the emissions, both in terms of the behavior of the emissions, where the emissions are occurring, where the damage from the emissions is occurring, the extent to which that damage is transferable into monetary costs, and then, of course, over time, uncertainty about the cost of pollution reduction amongst firms also plays a role in all of this. Another way to get at this particular problem is that instead of making emissions more expensive, we instead focus on the consumptive side of the product. So instead of taxing emissions, we tax the goods that create the emissions. The problem with this is that this situation is only efficient if every purchased unit creates the exact same amount of marginal damage, which is true in the context of certain types of emissions. But even like if you take gasoline as an example, some cars are more fuel efficient than other automobiles. And so if you put gasoline into, for example, a hybrid vehicle, each gallon of gasoline that goes into the hybrid vehicle is going to produce lower damage than every gallon of gas that goes into, for example, a Hummer. And so in that situation, because you have a greater damage being caused by a gallon of gasoline in the Hummer than you have in the hybrid, then you could have a situation where the marginal damages are different. Now, of course, the argument is often made, well, the person who drives the hybrid is going to pay a lot less for gasoline, and the person who has the Hummer is going to pay a lot more for gasoline, and there's sort of a hope, and I say hope here with quotes, that will sort of, become efficient over time. But it is a little bit of a problematic nature. With a product charge, you really need each unit of the product consumed to generate roughly the same amount of marginal damage. Otherwise, the tax is going to potentially have distortionary effects. For example, does it make sense that someone who drives a hybrid vehicle pays the same gas tax as someone who drives a Hummer, right? From a purely economic perspective, the answer is no, because the Hummer gallon of gasoline produces more damage than the hybrid does. So in an efficient perspective, it would actually make more sense for the per gallon of gasoline emissions charge on the hybrid to be lower than it is for the Hummer. Okay, so that's going to wrap up this video. I'm going to stop this here. It's already gone on a little bit longer than I intended, but the whole point of this is just to get you to wrap your head around the idea of optimal pollution, how we think about optimal pollution, and again, it depends upon what type of pollution we're talking about. Stock pollutants versus fund pollutants, and then beyond that, what are the potential problems with emissions charges and cap and trade programs, those market-based mechanisms that, again, economists tend to favor because they have this cost-effective component. As we've previously discussed, market-based mechanisms are generally preferred by economists for fund pollutants because they have lower administrative costs, they have lower regulatory costs. It's much easier to create a tax and put it into a market and kind of allow the market to react in its own way to the tax than it is to have an entire regulatory apparatus which is there sort of mandating specifically what the emissions would be, for example, at every individual firm. And the same thing goes for a cap and trade program. The idea is that once you allocate those pollution permits across the firms, and then you allow those firms to engage in profit maximizing pollution permit trading, what you will arrive at is the natural cost-effective solution to the optimal pollution problem. In a sense, what an optimal Pagovian tax and an optimal pollution permit in the cap and trade setup elicit is that second equimarginal principle response that we have established as the least cost abatement strategy. So once society has determined what the optimal level of pollution is, and in order to do that, it has to know what the sources of pollution are, how the pollution behaves, what type of pollution it is. This will define not only which policy society should use to reduce that pollutant, but will also define how each firm in the polluting industry is likely to react to different types of policy. One thing we know for sure is that in the absence of any type of policy, firms are very reluctant to abate their own pollution, again, because it puts them at a cost disadvantage with their competitors. And so the need for some form of environmental regulatory apparatus is that actually acknowledges the profit maximizing behavior of firms, and that without any sort of regulatory apparatus, whether it's a command and control mandate system or whether it's a market-based system with a tax or with a cap and trade, is that policy is needed in order to get pollution reduction. Again, these are market failures and we need effective policy. Now, the trick is how do you avoid policy failure? Right? What are the ways in which we would reduce policy failure? And this will be what we talk about for the remainder of the class.